simplify, these are the carbon materials. And we know how much we use carbon for different things. Materials application, tire application, filter applications, many things. So we can use soil amendment, fertilizer and other things. So let's focus on that. Adsorption, temperature control, organic contaminants, increased soil, soil amendment, adsorption, etc. So it's a very good system you can use that. And I have few slides different, but we'll go through that. Hydrochar, hydrothermal carbonization. How do you do that? So all these are waste material. You don't want to use high value material for making hydrochar. You don't want to use high value material for making biochar. Okay, you want to use waste material to add value to it. You need a pressure cooker or bar reactor, most commonly known, batch reactor. It can be continuous reactor also. The operating range is 250 per 320 at 280, 300 also. Sometime just water and you can carbonize and you can get hydrochar powder. Okay. Now this hydrochar, good application is solid because carbon percentage is better than biochar. So more like coal, it's stand-alone, it can be carried. You can still do soil amendments, depends on what you want to do, how much you produce and all. Or we can still do for cleaning water. We are talking biochar, production is little different. No water. One dry material. You can collect from the field and you can make biochar. So NCR, China part and all there we are burning. Some of the industry coming can make biochar. Okay. So you can have a pyrolysis unit. It can be mobile. You can move that place to place. And slow pyrolysis, fast pyrolysis, flash pyrolysis. Slow will give you more charge, and this is good for soil amendment, filtration application. Fast pyrolysis will give more oil. You will look at economics, do you have enough feedstock to go in oil direction or not? And some gases definitely. These gases typically in pyrolysis unit recycling back to the body. You see a pyrolysis unit, typically gas goes back, but still it has calorific value. You begin recycling, then you get cleaner gas and more CO2. This is the difference between hydrochar and biochar, how they produce. If you have a waste material, if this is not dry, if you are doing pyrolysis, not efficient, because you are heating water. And if you have a dry material, if you are doing hydrochar, again that's not right. You are adding unnecessary water and then doing the process. So this process both have applications. Now we should use our judgment which one to use. So the next thing comes, you want to make anything, you need to understand the material. Whether it's biochar or hydrochar, what it is exactly. It looks black and fluffy and all, but need to talk more detail than that. So it requires physical, chemical, structural analysis depending on what application we are looking. So proximate analysis, how many of you remember skills from yesterday? What was proximate analysis? Madam? What was proximate analysis? It's not exam, so 3 things, okay, if you don't remember, that's okay. Proximate analysis is 4 things. Moisture as fixed carbon and volatile. Yeah, as moisture, fixed and volatile. Now you can imagine why it is important. important. If you have biochar, you want to know, you are looking for electrode or what application, you want to know when this material goes for heating application, are there any volatile or not. So, approximate analysis will tell you. If you are looking for electrode application, you need more fixed carbon. Okay, you don't want to leach it out of the lab. So, you need approximate analysis. So, whether biochar or hydrochar, good way to start is approximate analysis. Remember, there is a carbon business, you need to know ultimate analysis, how much carbon it has. So, approximate analysis, ultimate analysis will characterize your biochar very basically, how much carbon it has and how much volatile it has, how it will behave in temperature. Few more things are important. You're looking for a sponge characteristics, porosity and all, then you need to measure surface area for the surface area. Right? Meter square per ton, how much force it has. So surface area is important. Porosity, bulk density and other things. So these are the characterization we have. And we do in our lab, we have the facilities. If you have some sample starting with that, if you can ship it and make it knowledge, then you can. Metal analysis you want to see because we are using this material. It has ash and we need carbonization. What happened to metal? Inside you know how much it is. You are going for electrode, what kind of impurity it might have. So you want to look at what metals it has. It's typically done with ICP, MS or ICP OES, mass spec, inductively coupled, plasma mass spec or optical spectroscopy. So this one we have in our lab. So we can tell 13 different metal what it has in one row. What kind of iron and other thing, how much percentage lithium it has. That's also good to know depending on what application. Physiochemical treatments we do, surface, how big the pores, how the surface do, ACM you can do, pH. When we make biochar or hydrochar, we want to put in soil. Let's say biochar. Soil pH is important, right? Different area, different soil pH. And you are going to mix biochar, soil, good amount, so pH will change, right? Impact pH. So we must know what is the pH of biochar, what is produced. In pyrolysis, we are going 500, 600 temperature. pH is alkaline. Because many ash components left carbon is there, more fixed carbon. So now you can match with the right soil quality, where which area have this soil quality, where we need pH high. If you are doing pyrolysis at little lower temperature, pH is not high in biochar. More like closer to neutral or acidic. If you have a hydrochar and you are using for soil element, hydrochar pH is low, typically 4 or around that. So now, where we use, you should know this is good quantity pH alteration will happen in soil. So this is acidic, good to know. So definitely look at these properties, and for analysis method of all these things, typically we follow a protocol, am I right? Some STM or some protocol. So IDEA, International Biochar Initiatives, IDEA is the body, professional body, where you will find all these protocol of analysis, how to measure pH of solids, right? This solid material. So protocol is called conductivity, cation exchange capacity, right? CEC, because when you are putting in soil, cation exchange happens. So you want to know that. So refer to IBI methods. They have all published open literature. Go to when you are writing manuscript and publishing, you can cite that IBI. Making biochar, what's going on, little details, what was happening, putting biomass and heating it, pyrolysis or hydrothermal, whatever, when heat, typically what we said, see that hemicellulose component will be hydrolyzed at lower temperature, using that water evaporates. Lignin degradation, you will see, yesterday I was looking very complex, it starts around 180, 200, and it keeps going. So it's a range band, there is no single point. When parallel diagram, yesterday again I was saying, when you characterize it, ultimately it's good to put in a when parallel diagram. That means it's by C ratio versus O by C ratio, atomic ratio, not percentage. Then you will see here your chart falls close to all. You can, it's way of data interpretation. You will see that. So pyrolysis where it fall, hydrochar, you can create stock, what kind of charge we are getting, what is the C ratio and all. You can do that. Surface area, typically we have seen that if you are doing hydrothermal, very low surface area. Why? And if you are doing biochar, compared to hydrothermal it is higher, but it's not activated carbon. 50, 60 meter square unit. So this is pyrolysis. Higher the temperature, surface area will increase, but it is still below 100. Right? But if it is a hydrochar, the surface area will be lucky to get 2 meter square. Why? Now we tell you. Think about the chemistry and tell me. Pyrolysis gives you higher surface area compared to hydrochar. Think of reactor, what's going on. In pyrolysis you are getting volatiles going out in gases. You are creating pores which gone out. In hydrothermal you have water which is trapping volatiles. When you are cooling, it is condensing back and then blocking your pores. It might be porous still, but pores are blocked. When you measure as it is, you will see very low surface area, because tar and other things will block. Now we want higher surface area, then we will do cleaning of pores by steam treatment or impregnating something and heating again. Okay, so that's way to understand. Now hydrochar, low pH. Why low pH? Again think of reaction medium. Biochar, things are going out. Hydrochar, water is doing hydrolysis and keeping organic acid inside. When you do hydrolysis, sugars, organic acid will come out. And they are still staying there, contributing to pH. So that's why it keeps low pH. Pyrolysis, more temperature, more carbon and volatiles going out, more ash component are staying there. So you will say it's close to basic. We are looking at carbon percentage. In hydrochar, things are condensing back, so carbon is getting stored, basically preserved solids, tar and tar. So carbon percentage is high. In biochar, more the temperature, less the carbon percentage, because you are using gas. So biochar as analysis, gas percentage is higher. In hydrochar, as percentage is low, because more carbon stage and as goes in water phase. So in fact, the water which comes from hydrochar, people can go store liquid fertilizer from all the nutrients. So that's the basic difference I'm trying to say. When you look at how to prepare your also topic. This one I showed you through one of them. So if you are doing hydrothermal, get hydrochar, higher carbon percentage, fuel application, materials application. Soil amendment you can do, but low value application for this, because you have a lot of carbon here which is better used than putting in off. And this is costly method to do than pyrolysis. And so pyrolysis you can do here, but hydrothermal you cannot do. You need a safety system, high pressure system, so it will cost. Why would you make costly char and putting soil? Okay, so it's better to look at how you produced and which is fit for what. So liquid, you remember, liquid came and can do anaerobic digestion and you can get biogas, and biogas can go back to somebody. If you are deciding a digester, and you are starting with digestion, the other one you are starting with hydrochar and liquid vaporization. If you have an existing digester and you want to use that, what waste you get from digester? The fibers, right? Solid you get, or biogas, liquid and fibers. Now that fibers can be used for hydrothermal making carbon. But that is also waste. Now that fiber can make hydrochar or composting or hydrochar. So that's another way to look at that. Now goes to biochar additives or hydrochar. You can have different tools. So you can do templating, coating, modifying surface, different metals, depending on what air purification or geolite and other things you can do. Once you have the finished stock of char, you can do so many things. You will do that's called further treatment or post treatment of biochar. I'll show you some examples. It's not from my lab, so I'll do other things. They can do soft templating, hard templating. You can do, once you template with certain material, you can carbonize pattern, you want to move it. You can get certain structures and you can get carbonized materials. You can play with the inner templating or covering with carbon. You have the base material and then you can do. So the basic chemistry is how char is made, and you can do a lot of modifications. Okay. I did these slides, you can look at that. You can functionalize biochar. You can add some functional group, oxygenated group and other things. So here I wanted to come. Biochar application you can do. This is raw, so soil, that's fine, but you want to better application, you can activate. You can do physical activation. Yes, increasing surface area. Gas purging, acid activation you can do. When you add acid to char, it further carbonize, like sugar and sulfuric acid. Alright, it will carbonize. You can do alkali activation, it will do shear kind of break some bonds, but it also increases surface area. So it depends on what we are looking for. We can infiltrate with potassium carbonate or and they mix together to increase surface area. So these are called post treatment of biochar, and you can do something for hydrochar. So take home message is you can get carbon as a feedstock. Now you decide what you want. That's the starting. There are different ways of making heat, supplying heat to it. If you are modifying biochar, acidic, removing an impurity, introduce acidic functional group, it will give. If you are doing alkaline, surface area will go, then it has oxygen containing functional group. Surface property is important when you put in soil. Remember, this is not coal. Look at ultimate analysis. Carbon percentage of hydrochar becomes 67, 70, 69, 86%. Nowhere close to 80%. It is not coal. It has oxygen. Those oxygen are functional group in form of carboxylic group, aldehyde group and all. So they provide some functional property on the surface. Okay? In biochar same thing. Carbon percentage and a lot of oxygen, mass and other things. So these are functional property gives you metal exchange capability. Metal will attach to this functional group. Okay? In soil it's called cation exchange capability. How much cation can be retained, drawn or be. So you can can do that alkaline treatment. Sometimes we can oxygenate ozone treatment sometimes. But ozone treatment will not do for field application. If you are looking at high value application, then surface want to modify ozone treatment, maybe higher percentage of oxygen, then it has applications. You need to think what you want. Metal oxides you can do, metal from that. Surface area can be increased, steam treatment, gas treatment. So this is a starting material for what we want to do. As it is, in soil it does not harm. It's carbon, it will help you retaining some of the nutrients, water. It will give you a surface for organisms to grow, microbiome to grow. Alright? So this is shown to be good material and very easy way of carbon sequestration. Why? Because this is not going to degrade. The life has been shown more than 100 years, close to 4. Surface may change, but carbon will stay. If it is compost, it will degrade in 2 years. But this is carbonized. So it's a carbon sequestration in short. It's easiest way we can do at our home. And I'll show you how can you build your own pyrolyzer in your community, nature, and spray in the garden. It's low tech, easy to do carbon sequestration, being environmental friendly. Then these are benefits why you do, so I'll list it. High value application, electrodes and other things you can make. Water filtration, dust and filter you can layer with biochar, you can do some better things. And in water filtration you need less compared to soil application. So how much char we put in soil, we have to do soil. Typically 1 or 2% in soil. Top layer you just mix 1 or 2%, not enough. And yesterday I was talking that the handling problem. We said fluffy application is difficult, so you want to make granules or something like that. So that is, we are not creating here. And this one shows that rice. So seedling this side was no biochar. This was biochar. See the broad difference. But this is not universal. Okay. You have to look at what quality, what feedstock you use and how much, but promising direction. So all these publications when you see that, don't take it universal. Because they prepare from certain feedstock is good for certain application. So when you really apply, you have to make your own and see that. Comparison, hydrothermal carbonation, we already talked. We just talked about all these things can go for what we are doing. Okay, so gasification will give you biochar, pyrolysis will give you biochar, thermal carbonization will give you biochar, when torrefaction will give you but less carbonized biochar. And then biochar yield will change depending on what temperature and how many. Yield is not that important here. If you heat at 200 degrees and make biochar, all yield will be there, it won't be carbonized, right? So how much carbon percentage will increase, that is. I already talked. If you are looking at HTC process, hydrothermal processes are more inefficient compared to pyrolysis because of phase change. HTC is a low emission process because of water is there to scrub the impurities. Let's focus on hydrochar. We have agriculture, carbon sequestration, phenol removal, soil amendment, activated carbon, biorefineries, dyes, gas exhaustion, energy production like green coal. So if you want to look at, have your own pyrolyzer and hydrothermal, you are looking at this design. This is typical pyrolyzer. You have a copper, blue dye that is the best for pyrolysis, where you get a nice mixing. You get char, oil and gas. You can tune this percentage what you want. For hydrothermal, you need just a vessel. You need a pressure cooker, that's all. Not much and solid liquid separation. But this pressure cooker is costly because a lot of metals to retain the pressure. And then you are generating liquid here. It can be liquid fertilizer, it can be mixed with wastewater, or it can be added in anaerobic digestion, but you have a liquid. People may question hydrothermal cannot be scalable. It is scalable. There are 5-6 plants in Europe, there are multiple coming in China. So differences, if you take both powder, what difference you will see? And I already told that hydrochar is low porous. This is more spherical in hydrochar versus here, more layered. Why you get spherical? Because when you cool it down, it condenses, and condensation gives you a speckle particles. H by C ratio, higher carbon percentage. O by C ratio, pH, mostly acidic, I told you, mostly alkaline. Aromatic groups are here and other things. So if you can do FTIR and look at the surface what functional group it has many functional group on the surface. Okay. So why it works with metals and other things for because they bind with these functional groups. When you make activated carbon, and we did in our lab and we compared it. So this is powder activated carbon combustion. Okay, this is biochar from corn and flour made as it is, no activation. So you see some functional group, which I was saying. Now we activated it, potassium plus. Now you see this is much closer to this. Alright? Got rid of many functional group by activation, it's more like activated. This was switchgrass, made biochar out of it, and H by C ratio you can see that. So if you want to store this organic material, very difficult to store, right? Lot of volume, biodegradation, the smell, things will happen. If you carbonize some pyrolysis of hydrocarbon, you will get a stable material. Transportation is easier, pelletization is easier. Okay. So the concept is, I yesterday talked also, you can have a different places of waste. Bring everything to centralize and you can do this. So if you can think of a pilot pyrolyzer, scale, carbonize and bring in the centralized facility. Now you've got a lot of biochar carbon and you